Hello, BMB510 MNE525 class. This is Tuesday's recorded lecture on operation parameters of bioreactors. We'll have another one on Thursday, plus an assignment. Thank you for being so accommodating in my canceling class for today. So we will get right into it. And recall what we talked about last week, where we first introduced cell growth and the concept of bioreactors. I talked about bioreactors as a vessel in which a bio-based process takes place, and that can use any type of cells for that bio-based process, or it could even be cell-free. So just a bag of enzymes or a bioreactor full of enzymes that are making a product. As a regular old reactor is just a vessel in which some reaction takes place. So a bioreactor is specific for biological or bio-based processes and reactions. A reactor could be biological, it could be chemical reactions. We don't specify. Fermenters in specific are vessels in which cells are grown. Usually fermenters are growing bacteria or yeast, making some kind of bioproduct. Oftentimes we think of fermenters in terms of alcoholic beverage manufacture. So these cells that are grown in those fermenters are yeast. But let's take a closer look at bioreactors, because that's what we're going to talk about this week. So a bioreactor is a vessel in which a bio-based process takes place. That we know. But what are some examples of bioreactors? Well, fermenters are an example of bioreactors. Blood oxygenators. We talked a bit about blood oxygenators. Those are examples of bioreactors. Artificial livers. Artificial livers can be bioreactors. Those have liver cells, and you can reroute body fluids through these artificial livers, and the liver cells will do their metabolic activity to basically act as your liver. Only it is a bioreactor that is outside of the body. Waste treatment apparatus often are bioreactors. There are often these cells that grow in biofilms on a membrane that will convert toxic compounds and waste to something a little more tolerable for the environment. So a lot of waste treatment processes use giant tubular membrane bioreactors. In this case, bioreactors that could fill the entirety of room 101A. That's how big they can get. And bioreactors can be categorized into several groups, and we'll see that presently. So, major types of bioreactors include mechanically stirred tanks, like CSTRs, and those are fairly self-explanatory. These are enclosed tanks that have a power unit that stirs an agitator or an impeller. There are bubble columns. These don't have that impeller or mechanical agitation, so there's no real shaft work being done. What happens is that gas is bubbled through the liquid in the bubble column, and the act of the bubbling of the liquid provides the agitation necessary. Loop reactors will often have pumps or jets for forced liquid agitation. You can imagine if a spa or something like that, with forced jets of forced liquid, if that was running a bioreaction, which hopefully it isn't, though that would be like a loop reactor with pumps or jets that forcibly move that liquid forward or around, or in often cases they're in a loop, so it's moving it around and around a loop. Membrane reactors are what are used in waste treatment. These are semi-permeable membranes. They facilitate mass transfer. These can also be used in artificial livers. So this allows for mass transfer, allows for diffusion of nutrients, but it basically it helps to contain your cells or whatever biochassis you happen to be using. So if you're using an artificial liver, the semi-permeable membrane will keep the liver cells in one place while you filter blood or fluid through, and the semi-permeable membrane allows for the mass transfer of nutrients or toxins. Microreactors are just whatever kind of reactor you can imagine here in a very small size. These are quite popular if you are trying to figure out what fermentation conditions or what bioreactor conditions are most suitable. So you can do a lot of microreactors at once, and then you can figure out the fermentation parameters and then scale up to, say, a mechanically stirred tank, bubble column, or whatever. There are other types of reactors that we won't talk about, and we won't really talk too much about loop reactors either, but we will talk about the others to some extent. There are gas-liquid interface reactors, there are rotating disk reactors, but we won't spend too much time with those. Those tend to be highly specialized. So what is required for bioreactor operation? So you need knowledge of a lot of things, and a lot of stuff we've already talked about in class these days. We have talked about mass transfer. You need a knowledge of mass transfer. You need a certain knowledge of heat transfer, because heat will be produced in a bioreactor. You of course need a knowledge of biochemical reactions, especially the biochemical reactions that go into making your product. Also the biochemical reactions that go into keeping cells alive. And you need a knowledge of fluid dynamics, and you can see in this schematic here that there are a lot of pumps and a lot of mixing going on, sparging, pumps for filtrate, pumps for the bleed, and pumps to keep feed coming in. All of these require a certain knowledge of fluid dynamics to operate properly, so you need the knowledge of that, as well as the knowledge of cell growth kinetics if you are using bioreactors with cells. And among these, we have many different types of modes of operation that we can run. So we can run our fermenters or our bioreactors in a batch manner, and we talked a little bit about batch processes last week. We could also try semi-batch. Those could also be known as extended batch or fed batch, where it's basically a batch process, but we are making some additions and possibly some subtractions over the course of the entire fermentation. And then of course there's a continuous stirred tank, or the CSTR. And then we also have something called the continuous plug flow reactor. Okay, so for batch processes, or batch bioreaction here, what initially happens is that we feed all the reactants and we inoculate with cells if we are doing a fermentation. So that everything is fed initially, and then the thing is allowed to run. We close, like I say, we close the lid and allow the process to run. You know, we have a certain amount of biomass, a certain amount of substrate, and that certain amount of substrate is hopefully going to get converted to a certain amount of product. So we let that happen, and then once the fermentation is done, we recover the product plus the biomass and whatever else is in there. We recover that batch-wise. So we put it all in, we take it all out, much like we would do if we were making soup, let's say. Semi-batch is slightly different. Semi-batch, we're adding reactants semi-regularly. Maybe we're adding substrate for growth and production. Maybe we're also adding some biomass, who knows? It depends, but we're adding it fairly regularly, semi-regularly. And fed batch, you're doing this at a regular basis. Extended batch is more of maybe once or twice throughout the whole fermentation. Regardless of how often reactants are fed, sometimes they're fed continuously. You recover the products, we recover the products in a batch-wise fashion. So it still has the name batch, and hence we call it semi-batch. So in both the cases of batch and semi-batch, we are recovering the products from the fermentation broth, from the fermentation media. We're recovering them in the batch-wise fashion. We're taking the entire volume and getting out our products. And so you can see this here graphically. If we look at the bottom graphs here, we look at the feed rate over time here on the top graph, and the volume of the reactor over time here in the bottom graph. We can see in a batch process, the feed rate is constantly 0. Nothing is coming in, nothing is going out. So we have a feed rate of 0 over the entire course of the fermentation. We just put everything in and we shut the lid. And the volume consequently does not change as we go through the entire fermentation. Again, nothing is coming in, nothing is getting taken out. So the volume remains fairly constant throughout the entire process. And so for something like a repeated batch, which is akin to what I call extended batch, we have, we start off in batch mode, and we don't see a change, at least initially, in the feed rate in or out. But at a certain point, we're doing some media exchange, so we take away a certain amount, and you can see that shown here by this dip into the flow out, and then we put new media in with new substrate. We put it in, and then the volume goes back down to the the volume that it was at when we began. So you can see here, you can see this via the volume, where initially we have a certain volume. When we remove some of the media, the volume goes down, but then we add that volume back in the form of fresh media, and then we're back, the volume is back to where it was in the beginning, and then we can do that again later on in the fermentation. But we basically end up with the same kind of volume where we started, although we have made some exchanges of media. We've gotten out some of the spent media with all its cells and its product, and put in fresh media that has a bunch of new substrate. And then that new substrate is converted to product. We take out the media again, it's got product, it's got cells in it, and we add fresh media. And then we do that again till the end of the fermentation, where we will then recover our product in a batch-wise fashion. Fed batch is a little bit different than that. Essentially all we're doing is feeding, a slow, steady feed. And initially, the feed is not changing. There's no feed at all, nothing in, nothing out. But at a certain point, we start the feed to make it a fed batch process. And then the feed rate goes up, and then continues, and then goes up and up until the end of the fermentation. And thus, the volume, you can see, begins to increase over the course of the fermentation until we end at a volume that is a lot higher than where we started in the fed batch process, but we still are recovering our products. We're still recovering this whole thing in a batch-wise fashion. CSTRs, or continuous stirred tank reactors, are different. These reactors, the contents are perfectly mixed and uniform throughout the reactor. The composition of outflow, we're feeding stuff in and we're taking stuff out continuously, and hopefully the volume inside the reactor isn't changing, and hopefully the other parameters aren't changing. Because the composition is constant, it should be at steady state. These types of reactors run best at steady state, and so that's what we hope to achieve if we are running a continuous stirred tank reactor. So you can see in this schematic we have substrate and potentially also biomass coming in at initial concentrations. Coming out, we might have we will definitely have a certain amount of biomass. We might have a certain amount of substrate, and we hopefully will have a certain amount of product as well being fed off in the continuous process here. There are more than one type of continuous reactors. There is what is called a continuous plug flow reactor. And now plug flow, we talked about Poisson flow a lot when we talked about fluid dynamics. We didn't talk a whole lot about plug flow. Plug flow is idealized flow. And what it is, it's a uniform fluid velocity across the entire channel of a tube, or in this case, a tubular bioreactor. And what we are seeing is no mixing in the axial or the radial directions of this bioreactor. So the only mixing that's occurring is in the direction of flow. The concentration of products and reactants will change along the flow direction. So you have reactants coming in the plug flow reactor, which are being converted to products throughout the length of this reactor, and then coming out the other end are your products. Concentrations are uniform in the direction perpendicular to flow. And so that's what we mean by no mixing in the axial radial directions. The concentrations are uniform in these places. And so in a batch reactor, we have no mass entering and we have no mass leaving during the fermentation. Fed batch, extended batch, those do have mass entering, but nothing is leaving during the fermentation usually. And so material balance for a reactant, let's call it A, would look like this. We have the rate of reaction with A times the volume, whatever the volume is the reactor, is equal to the volume times the change in the concentration of A over time, which could be equal to the volume times the initial concentration of the reactant multiplied by the change in the biomass, or the fractional conversion. X in this case is the fractional conversion of A over time. And this is under constant liquid density, which we can assume in most cases. And so Ra, as I said, is the reaction rate. V is the liquid volume in our fermenter, in our reactor. Ca is the reactant concentration in this case, so we'll look at the change in Ca over the change in time. Xa is not biomass, like I initially misspoke. Xa is the fractional conversion of A, and that is defined as follows. So we have the initial concentration of A minus the concentration of A at time t, whatever that is, divided by that final concentration of A at time t. And so we can look at different orders of reactions. We can look at first order, we can look at second order, we could even look at reactions that use Michaelis-Menten kinetics. And the rates, as well as the things we need to take into consideration, vary depending on the order of the reaction. And we will assume irreversible reactions. So in the case of irreversible first order reactions, where reactant A is converted to product P, the reaction rate can be given as follows here. We have the reaction negative Ra is equal to the negative change in the concentration of A over time, which is equal to K, our reaction constant, times the concentration of A. And so we can now determine the batch reaction time using this equation here. Again, we have our fractional conversion of A, and it's equal to the first order rate constant, which are in units of per second, times the time, t, whatever that may be. It's a little bit different for second order reactions. Again, we will assume it's irreversible. Two reactants, A and B, are being converted to product P. And the rate of reaction for these would be the change in, the reaction rate of A, negative Ra, is equal to negative the change in concentration of A over time, which is also equal to the negative change in the concentration of B over time. You can see these are stoichiometrically equivalent here, A and B, so 1 mole of A plus 1 mole of B will give us 1 mole of P. And that's going to be equal to the rate constant, the second order rate constant, multiplied by the concentration of A, multiplied by the concentration of B. And we can determine the reaction time using this equation, which is a little bit more complicated because now we have two players here. We have A and B. So we have to take into consideration the fractional conversion of A as well as the fractional conversion of B rather. And so in here you can see the CaO is the initial concentration of A CBO is the initial concentration of B. CA and CB are the concentrations of A and B at time equals T. Okay, so for Michaelis-Menten kinetics, we can consider different equation for batch reaction time. So there's no first order or second order constant. There's no small k here. All we have is our Michaelis-Menten constants, our parameters Km and Vmax. So we can use this equation here if we are considering a reactor that's running in Michaelis-Menten kinetics. So we have our initial concentration of A multiplied by the fractional conversion of A minus our Km times the log of 1 minus the fractional conversion of A is equal to our Vmax times our batch reaction time. The liquid composition in our continuous stirred tank reactor is uniform. So whatever is in our reactor is going to be equal to that of the exit stream. Accumulation of anything, accumulation of change in rates of accumulation of things are zero at steady state. And for CSTRs, we usually want to be at steady state. So we can look at a material balance for our reactants, or reactant A in this case, in a CSTR. Will give us this, where we have the volumetric feed rate, which is the rate at which liquid is going in and coming out, is multiplied by the initial concentration of A minus the feed rate times the initial concentration of A again times 1 minus the fractional conversion, which is equal to the negative rate of reaction times the volume of our bioreactor here. Okay, so you can see, this is a material balance here. What are our different terms here? We've got two terms that are equal to the rate times the volume here. What are they? Well, our first term here is the input term, which would be the initial concentration of A is coming in the feed, and this term here is our reaction type term, where we have our feed rate times the initial concentration, and we're looking at the fractional conversion rate. So this is our conversion / output term here. Both of these things are rates, and those will give us our rate of reaction in terms of whatever our volume is. When we think about continuous reactors, we think about different rates. We also think about volumes and time. So we always have those terms in play when we're talking about a continuous reactor. In the case of a CSTR, we can think about the residence time, which is how long your average stay of biomass and product and things like that are in the CSTR, and that is shown by tau is the residence time, which is the volume of the reactor divided by the flow rate. So how long on average will things stay in the CSTR to react and to make their products and things like that. And if we're talking biomass, how long will they be allowed to grow inside the volume of the bioreactor. And that can be shown by, in this case, it can be shown by the initial concentration of A times the fractional conversion divided by the negative rate of reaction here. The reciprocal of this tau, this residence time, is the dilution rate, which it literally is this flipped upside down, the feed rate divided by the volume, or it's the 1 over tau here. So you may see this residence time and say, well, we have this negative term here, so isn't this tau going to be negative? And how can we have negative seconds? Well, the rate of reaction of A, we are depleting A. So this RA is going to be negative anyway. So this will just make it positive, giving us a positive tau. If we have irreversible first order reactions, we can use the residence time and get, or we can get the residence time by our first order rate constant and our fractional conversion here. So XA divided by 1 minus XA. With Michaelis-Menten kinetics, it's a little more complicated. We need Vmax. We have an initial concentration and a fractional conversion term, plus our Km, and again, more fractional conversion. Okay, so let's consider a plug flow reactor. Again, this is a plug flow, a continuous plug flow reactor. And we can see the material balance for our reactant A in this case is a little bit different. You know, we still have a feed rate times concentration, but we have a little bit of a different term here, where we have feed rate times concentration plus the change in concentration. And if you recall, in a plug flow reactor, the concentration is going to change as the reactants move down the plug flow reactor and become products. And this is equal to the negative rate of reaction of A times the change in volume. And so for a differential volume element, or dV, of the plug flow reactor, this is perpendicular to the flow direction. Our residence time is still volume divided by feed rate, just like a CSTR. But for a first order reaction, we can determine our residence time as such here. For second order reaction, here we have, again, a little more complicated. You've got A and B, so you're considering the concentrations and the fractional conversions of both. And for Michaelis-Menten kinetics, here we have the Km and Vmax terms in these residence time equations as well. Okay, so here is an example. We are going to compare CSTRs and PFRs. CSTRs are the continuous stirred tank reactors, and PFRs are the plug flow reactors. So we have a feed solution that contains reactant A. We've talked a lot about reactant A today. Is fed to either a CSTR or a PFR at volumetric flow rate of 0.001 cubic meters per second. A is converted to P, so this is a first order reaction in the reactor. The first order rate constant, or K, is 0.02 per second. We want to determine the reactor volumes of the CSTR and the reactor volume of the PFR that would be needed to obtain a fractional conversion of A, or XA, of 0.95. So almost all the A is converted to product. And so here are our data here I'm showing you. We have the XA, we have the first order rate constant K, and we have our flow rate in both the CSTR and PFR. This is our feed rate. So we want to calculate residence time. So how do we do this? So we use tau, our equation for tau, and that is the fractional conversion of A divided by 1 minus the fractional conversion of A multiplied by 1 over the rate constant. And so we plug all those values in and we get 950 seconds. So that's our residence time for a CSTR, is 950 seconds. So we can calculate our volume with this, because tau is equal to V over F, and we end up with a volume of 0.95 meters cubed. So that's for our CSTR. What about for our plug flow reactor? So again, we've got the same parameters here. We want to calculate the residence time. We use a bit of a different equation, as you know. And so we plug in our fractional conversion. We plug in our first order rate constant. We end up with 150 seconds as our residence time. We calculate our volume. Again, V is equal to F multiplied by tau. We get our volume of 0.15 meter cubed. Okay, so you notice there's a bit of a difference in the volumes, whether we're using a CSTR or a PFR. So volumes needed for 95% conversion of A, For CSTR, it's about 0.95 meter cubed. It's about 1 meter cubed almost. And for a plug flow reactor, it's significantly less, 0.15 meter cubed. So the required volume for the PFR, I don't need to say, is much smaller than that of the CSTR, and we're to get us an equal fractional conversion. In general, this is usually true. Larger volume is required for a CSTR than for a PFR. And so, why are they larger volumes? Well, in the CSTR, you have the feed, the unreacted A, in this case, the unreacted reactant, is coming in and it gets diluted and it gets mixed. And because of that, you need a longer residence time, you need a larger volume. In a PFR, there's no mixing in the axial direction, so the localized reactant concentrations tend to be higher. So you tend to need less of a volume in a plug flow reactor. And this is good if you're starting up a company and you want to save on capital costs. Well, I'll use a plug flow reactor in that case, as opposed to a CSTR. I can get away with much less volume and keep my capital costs down to a dull roar. That's fine. However, if you're doing a process and all you have lying about is a CSTR, well, you got to use the CSTR. So it all depends on what you're doing. But in general, it is usually seen that a PFR requires less volume, which is neither good or bad. It all depends on what you're doing. So it's always dependent on the process. Okay, so let's talk about we talk about bioreactors. Let's talk about bioreactors that use immobilized catalysts. So these are catalysts like enzymes or cells that are basically packaged in some kind of particle, some kind of polymer particle or activated carbon type particle where they can basically do one job. They don't have to grow, they don't have to make DNA, they don't have to faithfully replicate plasmids. They have one job. They convert substrates to products. They're stuck in place. They don't waste ATP swimming around. They convert whatever substrate you put in. As soon as it comes in contact with a catalyst particle, it gets converted to product. So for these, and this is why they're called heterogeneous reactions, there's a diffusion component and a reaction component. You can see here's a substrate particle or a substrate kind of flowing and diffusing into this particle here, and these are immobilized enzymes or cells. The immobilized biomass will convert substrate to product. This is the orange thing, and then the product will diffuse back out into the bulk liquid. And so these heterogeneous reactions occur in the presence of a significant concentration or temperature gradient. For most bioreactors, concentration gradients are what is common. And so that's what we will focus on. Concentration gradients of the substrate are common when reactions involve immobilized enzymes. And immobilized enzyme reactions are fairly common. We typically don't see temperature gradients in biological reaction, so we focus on concentration gradients, since they are common when we deal with immobilized enzymes or immobilized cells. And we can immobilize our enzymes or cells in a variety of ways. They can be immobilized by entrapment within some kind of matrix. Typically those matrices are things like alginate, agarose, things like that, polymers, polysaccharides even. Or you can entrap them in porous solids. And this is typically done with enzymes, although it could be done with cells. They can be entrapped in solids like ceramics, glass beads, things that have a bunch of surface area and a bunch of crevices and pores where you can entrap these enzymes, and the substrate can diffuse into the particle and through the pores and then react, and the product diffuses back out. So the substrate must find its way to the biocatalyst for the conversion to take place. And so because of this, we inevitably are creating a concentration gradient, where the bulk liquid has the higher concentration of substrate, and near and in the particle has a lot lower concentration of substrate. So we are diffusing from the bulk liquid to this, we'll say, the center of our immobilized enzyme particle here. And so the path of these reactants can be long, and it can even be quite difficult. It can be fraught with resistances to diffusion, to mass transfer, to get the substrate to where it can be at the active site of a catalyst surface here. So it's going to start by diffusing through what we call a boundary layer, and more on that in a minute. It'll diffuse through the boundary layer and to the surface of the catalyst, and if it's going through a porous catalyst, it's going to work its way through pores, snake its way through the tortuous pores to get to an enzyme in the center. Once it finally reaches the center and hits an active site of an enzyme at the surface of a catalyst or on the surface of one of those pores, the substrate is turned into a product. There's a chemical reaction. The product then has to desorb from the surface, again diffuse through the pores, again diffuse through this boundary layer surrounding the particle, and then back into the bulk liquid. So it's got a ways to go before it can do things. So this is a lot different than just having a tube or a fermenter or a beaker full of aqueous protein, where we just throw some substrate in and the reaction happens almost immediately, and is really only dictated by how fast the enzyme can make the reaction go. Here we have a reaction component, and we also have a diffusion component, and the diffusion component can be quite significant, especially when we talk about the liquid film. So what is this liquid film that I talk about? This is a boundary layer. It's this thin, poorly mixed liquid film that surrounds any spherical catalyst particle, or any shaped catalyst particle, honestly. Most cases, and a lot of cases, mass transfer across the boundary layer is the rate controlling step. So how fast will the substrate traverse across this boundary layer? That determines how fast the reaction will happen. The rate of decrease of, again, let's say reactant A per unit liquid volume, or negative RA, is equal to this KLA multiplied by our concentration of A in the bulk liquid minus the concentration of A at the surface of the particle. So KL is this liquid film mass transfer coefficient. So there's a special mass transfer coefficient for these boundary layers because it is so poorly mixed. Our A is the surface area of the entire catalyst or particle, and we'll look again, with the bulk liquid and the surface of the catalyst, we're looking at a concentration gradient. And so we can get an apparent reaction rate. It's kind of hard to get an actual reaction rate. We would have to delve into the inner workings or the innermost reaches of the particle in order to get a real reaction rate. But we can get a pretty close approximation here in heterogeneous reactions, looking at an apparent reaction rate. And especially for reactions that are controlled by that boundary layer resistance, an apparent reaction rate depends on this dimensionless number called the Damn-Cooler number. And you can calculate the Damn-Cooler number here by looking at the maximum reaction rate divided by this mass transfer term, which has KL, it has the surface area, and has the bulk concentration of substrate. This is the ratio of the maximum reaction rate to the maximum mass transfer rate. And so we can look at the Damn-Cooler number and get an idea of what's going on. The mass transfer rate, if it's much slower than the reaction rate, our Damn-Cooler number will be much greater than 1. And that'll mean that the apparent reaction rate becomes almost equal to the mass transfer rate. When Damn-Cooler number is greater than 1, in this case, we can use this. We can look at this as negative RA, our reaction rate, is equal to our mass transfer, our KLA, times the concentration. Reaction rate, however, is limiting when the dam cooler number is much less than 1. Okay, and so we are looking at diffusion effects. The resistance to mass transfer within the catalyst is going to result in lower apparent reaction rate. So the substrate has to traverse either through a gel particle, a polysaccharide particle containing immobilized cells or enzymes, or it's got to diffuse in through these pores to get to enzymes on the surface in the center of the particle. So basically all it means is there's a lower supply of reactants reaching the catalytic site because it has to diffuse through stuff, and that stuff results in resistance to mass transfer. There are long diffusional paths resulting in high resistances. And again, you see these pores are quite branched and tortuous. The resistance applies both to reactants getting to the enzyme active site, and it could also apply to products, especially if the only way we have to measure our reactions is by looking at how much product has been formed and is in the bulk liquid. So basically the reactant has to diffuse through, then react, then it has to diffuse back out. So that will significantly change the apparent reaction rate compared to if we just had free enzyme floating around in our media. Okay, so a way to think about this is via effectiveness, or basically effectiveness of mass transfer and reaction. So we have long tortuous paths for substrates and products to take, and that results in resistance, as I said. The overall effects of these involving mass transfer and reaction rates can be expressed by what is called an internal effectiveness factor, and that can take two forms here depending on what book you're looking at. It can either be this Greek letter here or EF, effectiveness factor. And you can calculate effectiveness factor where we look at the apparent reaction rate divided by this RAI, which is the intrinsic reaction rate that excludes any mass transfer effects within catalyst particles. So it would be some kind of ideal reaction rate. So we have our apparent rate and our ideal rate, and that'll give us our effectiveness factor. If there's no mass transfer resistance, then our effectiveness factor is equal to 1. Then that probably means we don't really have an immobilized enzyme system. Okay, so effectiveness factor will basically decrease from unity, i.e. 1. It'll be less than 1, with increasing resistance to mass transfer. The more resistance, the further away from 1 we're going to get. That is the resistance within the catalyst particles. But this is the internal effectiveness factor, internal to the catalyst particles. The degree of decrease of our effectiveness factor is going to be correlated with this dimensionless parameter. It's called the Thiele modulus, and it's denoted by this Greek letter phi here. Thiele modulus involves the relative magnitudes of reaction rate and the molecular diffusion rate within our catalyst particles. And here's how we can think of Thiele modulus in first order kinetics here. So in first order kinetics, we can think of Thiele modulus in terms of the particle radius and the square root of the first order reaction rate divided by what we call the effective diffusivity. Now the effective diffusivity is very specific to the system we're working with. It is based on the overall concentration gradient inside the particle, but is specific to the reactant. It is also specific to the medium that the reactant will be passing through. And so we can look at the radial distribution of reactant concentrations within our spherical catalyst, and you can see they would probably take some kind of, in most cases, if we were to plot them out, concentration versus length, from outside to inside the biocatalyst and back outside again, we would see the highest concentrations in the bulk liquid, followed by a decrease in concentration as we go through the boundary layer and get to the surface of the catalyst. plus again a further decrease in concentration of our reactant as we get towards the center of the catalyst, leading to an increase as we get closer to the surface of the catalyst, again an increase as we go towards the edge of the boundary layer and into the bulk liquid where we have our highest concentration. And so Ca star is this ratio of reactant concentration at a distance from the center of the sphere, and CAS is our concentration of A at the surface of the catalyst. And so Ca star can give us this ratio in the form of this hyperbolic sign 3 times the Thiele modulus times R star, which is the reaction, which is the radius ratio. Our small radius is indicating where we're measuring our Ca. So Ca is the Ca at radius of small r. Big R is the overall radius of the spherical biocatalyst. So that's what R star is. So we've got 2 ratios here, and R divided by R star hyperbolic sign of 3 times the Thiele modulus. And the hyperbolic sign can be expressed using this mathematical expression here. So if we have steady state conditions, the rate of the reactant transfer to the outside surface of the particle would correspond to the apparent reaction rate within the particles. And so for first order reactions within spherical particles, we have an effectiveness factor that looks like this. And instead of the hyperbolic sign, we have this hyperbolic cotangent, which can be expressed using this mathematical expression right here. And again, we're taking into account the Thiele modulus while we do this. And we can, for low values of Thiele modulus, the effectiveness factor is almost 1 here. So we look at Thiele modulus down to 0.1 here or so. Effectiveness factor is almost, as we say, unity, 1. Our effectiveness factor decreases in proportion to the Thiele modulus. So for higher values of Thiele modulus, as you can plainly see in this graph, doesn't matter the geometry, higher Thiele modulus, lower effectiveness factor. Thus, effectiveness factor decreases for a number of reasons. It can decrease with increasing reaction rates. It can decrease with increasing radius of catalyst spheres, so the bigger the catalyst. It can decrease with decreasing effective diffusivity of reactants within the catalyst. And this makes sense. The increasing radius of catalyst, obviously there's going to be more barriers to diffusion because substrate and product are going to have further to go. And certainly if you decrease the effective diffusivity, it's not that substrate and product will have further to go, it's just that they'll have a harder time getting to the surface and being part of the observed reaction rate. And so we talk about immobilizing things like enzymes or cells on these biocatalysts. There are many ways we can do this. There are irreversible and there are reversible methods that allow us to immobilize enzymes and biocatalysts. Some irreversible methods include covalent binding of the enzyme to the catalyst surface or the pore surface, entrapment in beads, fibers, polymer type things, microencapsulation in things like agarose and other polymers, cross-linking to each other. These are all irreversible ways that enzymes can be immobilized. More reversible methods include simple adsorption to the surface of a catalyst particle or the surface of pores of a catalyst particle, ionic binding to a similar catalyst particle, affinity binding. We have a catalyst particle that has antibody all over it and will bind an enzyme holding it there, or chelation or metal binding. We have a metal binding domain on an enzyme and then it binds to the metal on the surface of a catalyst, or maybe the catalyst itself is made of the metal. And we can do disulfide bonds, which are covalent bindings, but they are reversible because we know how to undo disulfide bonds. So we can link an enzyme using disulfide bonds. So we have irreversible and reversible methods for immobilizing enzymes. And we need to take into account, when we're talking about enzymes on a particle, we can take into account Michaelis-Menten. If we're talking about an enzymatic reaction rate here. So apparent rates will decrease with immobilized enzyme particles due to that increased mass transfer resistance. And now it seems like I've said that quite a bit today, but you can't stress that enough. So we're looking at mass transfer resistance of substrates as they go into and through a particle. And the Thiele modulus of spherical particles that have immobilized enzymes with Michaelis-Menten kinetics. The Thiele modulus looks like this. Again, instead of a first order or a second order reaction rate constant, our little k, we need our Vmax and Km here, and we can see those in the Thiele modulus equation right here. The values of our effectiveness factor are going to decrease with increasing reaction rate and or increasing concentration of immobilized enzymes. Effectiveness factor also decreases with increasing mass transfer resistance. And so let's look at an example. We look at Thiele modulus, we look at effectiveness factor, and we look at rate of reaction in immobilized enzyme beads. And they have a diameter of 0.6 centimeters. They can convert substrate to product using Michaelis-Menten kinetics. And so we have some data on that. We have our Km, we have our Vmax, we have a bead density. Our density is 1,000 kilogram per meter cubed, and we have our effective diffusivity. And we want to determine the effectiveness factor, our EF, and our initial rate of reaction when we have a substrate concentration in the bulk liquid, our CAB, is equal to 0.6 kilomoles per meter cube. So here's our data. I changed the diameter to radius. Our particle radius is 0.3 centimeters. We have our Km, Vmax, bead density, our effective diffusivity. We have all that. So we want to find the Thiele modulus. So we use our Thiele modulus equation that we got from our previous slides, looking at the Thiele modulus equation in Michaelis-Menten kinetics. So we plug everything in. We have all this stuff. We have our R, we have our Vmax, we have our Km, we have our effective diffusivity. We can just plug all that stuff in. Okay, so one thing you will notice, and that I will mention right now, is that you see we have kilomoles, we have meters cubed, we have centimeters. Whoa, we need to do some conversions, don't we? Not so fast. We don't need to do conversions. If you look, in certain key places we have meters cubed, but those meters cubed are canceling each other out. Thiele modulus is a dimensionless number. Centimeters are canceling each other out. We are basically left with dimensionless number. We don't need to perform unit conversion here. So, I know this is kind of a tricky monkey wrench we're throwing into the works here, but we have a variety of different units. But we can see, if we look at the equation close enough and we look at the values here, that all these units are going to cancel out to give us that dimensionless Thiele modulus here. And so our Thiele modulus is 17.3. And now we need to use that to find our effectiveness factor. So to do that, we need a chart that looks like this. But first we need this thing called the beta factor. Now the beta factor, it looks at the Km divided by the bulk substrate concentration, our bulk concentration of A. So we get the beta factor. Our Km is 0.012 and our concentration of A in the bulk liquid is 0.6. We get a beta factor of 0.02. And now here is effectiveness factor divided by versus Thiele modulus, looking at a variety of different beta factors. Unfortunately, we don't have 0.02 here. It would be somewhere in this space here. But we can estimate it. We would use a different chart compared to this one. But we would be able to use that chart and get an effectiveness factor of around 0.5. So you can imagine the beta factor curve of 0.02 is somewhere in here, which would give us an effectiveness factor of 0.05. Okay, so we have our effectiveness factor, we have our Thiele modulus. What we need now is our initial rate of reaction. So this looks a lot like our Michaelis-Menten equation. In fact, it basically is, except for the fact that because we're considering immobilized catalysts, we need to take into account the effectiveness factor. If the effectiveness factor was 1, this would essentially be the Michaelis-Menten equation. But we know it's not, it's 0.5, so we need to multiply our Michaelis-Menten equation by 0.5 to get our initial rate of reaction, our observed rate of reaction. And so we do that, and we end up with 1.8 times 10 to the negative 4 kilomoles per meter cubed second. That is our rate of reaction. Okay, so let's talk a bit about aeration in reactors, in bioreactors. So in both stirred tank reactors, and we talked briefly about bubble column reactors, gas bubbles are rising through the liquid and to a certain degree aerating the liquid. Gas in bubble columns, the act of the aeration results in the mixing and the aeration of the fluid. In stirred tanks, we have help from the mechanical spinner, the mechanical agitator, that is allowing mixing of gas into the liquid. So bubble formation takes on extra importance in the bubble columns because essentially the bubbling is the means of agitation. And this is true for airlift reactors, which are a type of bubble column, which we might talk about later. But in the stirred vessel, we have aeration by bubbling using the gas sparger here, and we have mixing in a mechanical way using some shaft work. And so how do we determine how much gas we're getting in, how much gas is going through, and what are the aeration parameters of our fermentation or our fermenters under given conditions? With that, we can use what's called the gas holdup. The gas holdup is basically a volume fraction of bubbles in a gas liquid. And there are two different bases for which we can define this, defining gas holdup. And the total one is the total volume of the gas bubble / liquid mixture. And so that is pretty easy to see. You basically bubble gas through a column through a fermenter filled with water, and then you mark off what the total volume of that is. And then there is the clear liquid volume, which is basically the volume of water or whatever, which excludes the bubbles. And that you can get by just shutting the gas off and letting the air bubbles gas off, and leave out the top. Okay, so we can calculate these things. So if we calculate gas holdup using our basis of the clear liquid volume, we use this equation here, where we have this epsilon here is equal to VB over VL, which is equal to this ratio ZF minus ZL over ZL. So VB is the volume of bubbles. So you would add up the volumes of each individual bubble and get the total volume of bubbles, and VL is the volume of liquid. So again, you can get this. You can get the volume of bubbles. You turn on the gas to the rate you want it to be at. And then you look at the total volume. The VL is the volume of liquid, so that's before you turn on the gas. You measure the volume of liquid. With the gas, you have the volume of liquid plus the volume of the bubbles. So you can easily figure out the volume of bubbles, or at least get a good estimate. The Z's here, ZF is the total height of the gas-liquid mixture. So you see we have this see-through fermenter tank here. So we can measure the height of the gas-liquid mixture as bubbling is occurring through the water. And ZL would just be the height of the liquid, excluding the bubbles. So again, you turn off the gas, and you can easily get ZL if that makes any sense. Okay, now let's look at the other type of basis, the total volume basis. So in this case, we look at gas holdup defined as VB, which again is the volume of bubbles, and VL is divided by VL plus VB, or basically the total volume, the volume of liquid plus the volume of bubbles, and ZF minus ZL divided by ZF, which is the total height of the gas-liquid mixture, minus the total height of liquid excluding the bubbles, is divided by ZF. So you can see the subtle differences here. One, we're just looking at the bubbles over the liquid. We're taking those two things in isolation. Here we're looking at bubbles as a fraction of the total. And you notice the different ways in which we denote gas holdup based, depending on what the basis is. For the total volume basis, it's just simply epsilon. For the clear liquid volume basis, it's epsilon with a line under it. And those are the two different things there. Now, how do we measure gas bubble volumes? And again, I was trying to explain this, but probably tripping over myself and failing. Gas holdups can be attained by measuring ZF, the height of liquid including bubbles, and then ZL, the height of liquid without bubbles. So essentially the height of liquid in your fermenter while you're bubbling air through it. And then you shut off the air and get the height of liquid without bubbles, so while you're not bubbling air through it. And then a following relationship will hold. Again, this is our epsilon using the total volume, using the clear liquid volume basis, divided by our epsilon using the total volume basis, is equal to VL plus VB divided by VL, and it's going to be greater than 1. This relationship always will hold. The use of the total volume basis is more common in determining the gas holdup. I think basically because it's somewhat easier to do. Clear liquid volume basis can be more convenient, however, depending on the situation. But the use of the total volume basis is a more common way to do it. Okay, when we're bubbling air through a reactor or fermenter, we need to consider interfacial area. So there are two definitions of interfacial area. The interfacial area between gas and liquid, we can consider that per unit volume of the entire mixture with gas and liquid, or just per unit liquid volume. So basically we're either considering the entire volume, bubbles included, or only the liquid volume, excluding the bubbles. There'll be at least 3 methods to measure the interfacial area in the liquid gas bubble system. We could use a light transmission technique, which is akin to looking at particles in solution, like optical density. We could use a photographic method, which is as simple as it sounds. You take a picture of bubbles in a fermenter. Or we could use a chemical method, and we will talk about these methods right now. Using light transmission, we're basing that on the fact that the fraction of light transmitted is related to the interfacial area, and it's going to be related, will also include the light's path length. So this will be irrespective of bubble size. So you have liquid that has bubbles of air or some kind of gas in it. We shine light, we get a optical density like value, and that can be converted to the interfacial area of gas and liquid. Using the photographic method, we can look at a photograph, again, of bubbles going through a reactor. We can get the sizes and number of bubbles measured on photographs of bubbles. So like this, we can take the diameter and figure that out. Of course, there's going to be a wide distribution of bubble sizes, as you can kind of see here, and a wide distribution of bubble shapes. We can get a volumes to surface mean bubble diameter, what we call DVS, looking at the sum of the diameter of bubbles cubed and the sum of the diameter of bubbles squared. For this method, the interfacial area, our A, is going to be equal to the gas holdup divided by this DVS, this volume surface mean bubble diameter here. Chemical method is very common. It's based on the theory of enhancement factor, which I won't get into too much. But it's gas absorption accompanied by chemical reaction. And what that is gas absorption. We think about the gas film that surrounds every gas bubble. We're looking at gas that is basically being absorbed from that film and taking part in a chemical reaction here. So we have reactant A, which is being consumed as it crosses the gas-liquid boundary layer. So it's going from, here's the gas, it's at its highest concentration in the gas bubble, so we can assume this is oxygen, say, and as it crosses that gas film to get into the liquid, it is, again, poorly mixed here, so it's going down the concentration gradient, but we're seeing a decrease in concentration, and then till finally we're here, and then it's going to be pulled by absorption and reaction, and we see it's going to be converted from A to B. So a chemical reaction is taking place, which is pulling the gas, or the specific gas, from the liquid film, from the gas film to the liquid film to the bulk liquid, where the reaction will occur. The gradient concentration of A required for this diffusion will gradually decrease as you get further and further away from this interface. This is our gas-liquid interface here. And so essentially what you will see here is that the oxygen is being used in a reaction as soon as it is crossing the interface and hitting the liquid film. A common term in bioreactors is KLA, and this is the mass transfer coefficient. It is used to characterize the oxygen transfer capability of fermenters or other types of bioreactors. It's actually, KLA is made up of two terms, KL, which is the liquid phase mass transfer coefficient, and A, this interfacial area that we've been trying to calculate. Together they make a more practical volumetric mass transfer coefficient. Now we can measure KLA in a few ways. We can use the steady state balance method, which is basically evaluating KLA in a reactor that operates at steady state, and this is based on flow rates in and out and the known rate of mass transfer, oxygen mass transfer usually. In large vessels, this is not a practical method to use. An unsteady state mass balance method is also used, which involves the adsorption of oxygen or CO2, and that can be monitored by sensors. So if we have a probe that's measuring for oxygen, we can get our KLA based on the adsorption of oxygen onto the probe and the signal that we would get as a result. It needs to be sensitive enough, you have to respond quickly to rapid changes in concentration, should they occur. There's also the sulfite oxidation method of measuring KLA, which is based on the air oxidation of sodium sulfite, which you can see here, Na2SO3, to Na2SO4, or sodium sulfate. And this is done with a given concentration of sodium sulfate, or sulfite rather, and cupric ions, Cu2+. The value for Kl for the rate of the O2 absorption into the sodium sulfite solution is equal to the Kl for the physical oxygen absorption into the sulfate solution. So depending on your rate of reaction, you get a rate of absorption here. This yields higher KLA values than those compared to pure water because of the effects of these electrolytes here, sodium sulfite and or sodium sulfate. And so we can determine all this based on the chemical reactions that occur. There's also a dynamic method of KLA measurement. Again, we're using an oxygen electrode. This follows a step change in aeration conditions. So essentially we're turning the aeration off in a fermenter. The simple method will give us a reasonable result for KLA under the following assumptions. We'll assume that liquid is well mixed. We're assuming that the response time for the oxygen electrode is much smaller than 1 over KLA. And we'll assume that the measurement is performed at sufficiently high stirrer speeds to eliminate, or minimize anyway, boundary layers at the surface of our oxygen probe. So the state of our oxygen probe is pretty key here. And we're also going to assume that gas phase dynamics can be ignored. And so this is a graphical illustration of what that looks like. So we're measuring, using our probe, we're measuring the aeration of the liquid. Then we immediately turn the air off, and we see a decrease in the air concentrations in the liquid. We turn the air back on, and we eventually watch the air concentration in the liquid go back up to around what it was initially, before we had turned the air off in the first place. And so we can use this equation to determine the rate of change of dissolved oxygen. So the change in the concentration of oxygen in the liquid over time is equal to our KLA multiplied by this this factor here, which is the saturation concentration minus the actual oxygen concentration in the liquid. And you can imagine as the air is turned on, we're equilibrating once again, that this is going to change. And if we're talking about oxygen consumption rate of microbes and biomass, we have this biomass term here. If there's no change in our concentration over time, then the oxygen consumption rate multiplied by the concentration of biomass is equal to that KLA multiplied by our saturation concentration minus our concentration of oxygen in the liquid. And to actually get KLA, we plot our change in concentration over our change in time, and our slope of this curve would be KLA. Alright, so let's run an example where we calculate KLA in an aerated stirred tank. We have air bubbling into degassed water in a stirred tank. The oxygen concentration in water is continuously measured by an oxygen electrode. The equilibrium concentration of oxygen, which is in equilibrium with air under atmospheric pressure, our CL star in other words, is equal to 8 milligrams per liter. We can ignore the delay in response of the oxygen electrode, so we assume it's better than 1 over KLA. We want to determine KLA based on this and based on the data in the next slide here. So here are our data. We've shut our air off or turned our air on. We have a concentration of 0 at the beginning. We turn our air on and we see, every 20 seconds we take a measurement and we see the concentration increasing. Our saturation concentration is 8 milligrams per liter, so we're heading towards 8 milligrams per liter here. We're not dealing with cell growth, so we can ignore the QX term. So our change in concentration of air over change in time is equal to KLA multiplied by this gradient here, saturation concentration minus actual concentration. And so we integrate CL equals 0, starting at CL equals 0 and T equals 0, we get this equation right here. And so we use this equation and we use these data and we plot the log of this term here over time versus time, and we get a slope of 0.0217 per second, which is 78.1. Our KLA is 78.1 per hour. Okay, so on Thursday I will have another recorded lecture for you. We'll talk about mechanically stirred tanks. We'll talk about their dimensions, their power requirements, gas dispersion, more on gas dispersion. We'll talk about bubble columns. We'll talk about types of bubble columns, performance. We'll talk about agitation, We'll even talk a little bit about packed bed and a little bit about microreactors. So look for the recorded lecture on Thursday, and look for a small assignment that'll be due the following Thursday. And there is an assignment due this Thursday. Please bring it to my office when you can on Thursday or before.